What is up, everybody? It's Dan from SageMathTestPrep.com, and I have received a couple problems from one of my students. It is an Algebra 2 class that he's in right now, and these feature using the rational root test to solve each quadratic equation, and then we're going to sketch the equation. That is what the directions on the previous page of this packet say. So I'm a big fan of just kind of going through the motions in the order that they say. So they say rational root test, we're going to use the rational root test. So that's really the first thing we have to do. Also, I'm going to cover up this stuff because I think it's a little bit distracting, and we're just going to start purely from scratch. So the first function is obviously this one. And what I'm going to do is I'm going to rewrite it in a way that we can really study it. So we have f of x equals x cubed plus 6x squared plus 5x minus 12. And basically, when using the rational root test, you need to focus on the constant that's at the tail end, and you need to focus on the first coefficient. Now, the first coefficient is a 1. Okay, there's a 1 right there. And what you want to do is basically consider all the possible combinations of all of the factors of negative 12 over all of the factors of 1. Okay? So that's the first thing you want to do, is you want to find all the factors of negative 12 over all of the factors of 1, and then take literally every single combination into account. All right, now, if that's not clear, it will be soon. So factors of negative 12, obviously, there's going to be plus minus 1 and 12. 2 and 6 and 3 and 4. Now notice how I do this plus minus thing. That's going to be sort of, well, very important. Actually, when you do the rational root test, you got to do the plus minus stuff, right? 1, 2, 3, 4. Because it could be positive 1 times negative 12, or it could be negative 1 times positive 12, right? So you just have to sort of take all that into account. And we're going to put that all over all the factors of 1. Now, the teacher's being very nice. All the factors of 1 are just 1, right? 1 and 1. But we do, of course, need to remember it's plus minus 1. Now, seeing as how, it's plus minus, so it means positive or negative 1 over 1, positive or negative 2 over 1, positive or negative 3 over 1, positive or negative 4 over 1, positive negative 6 over 1, positive negative 12 over 1. Now, at the end of the day, we can ignore this 1 because anything over 1 is just itself. So at the end of the day, really, the factors of negative 12 or the factors of positive 1 are really just positive, negative, 1, 2, 3, 4, 6, and 12. Now let's make sure we're totally clear about what this means. What this means is that these are possible roots. Possible rational roots, okay, rational roots, okay. Rational, hopefully my student at home understands that means that it's certainly not an imaginary number, right? Rational numbers are not imaginary numbers. And it's also the case that they are numbers that could be represented by A over B in such a way that A is an integer and B is an integer. For example, 2/3 is a rational number. 12 over 1 is a rational number, and so on. Okay, so hopefully that makes sense. Moving on to this situation, what you have to do is test each one of these and see if you were to divide, the coefficients of this original function by any one of these potential roots, if you get a remainder of 0, then you know for a fact that it is indeed a rational root, that one of these numbers is indeed a rational root. And as my student at home knows, that's going to be a matter of busting out the synthetic division stuff. Now, what do you have to do first? Check the coefficients. Be very careful. First of all, are the exponents in descending order? Absolutely. It goes 3, 2, 1. And believe it or not, this is x to the 0 right here, believe it or not. So it does go 3, 2, 1, and then x to the 0 right there. So that's the first step. Now, if it was the case that, for example, the x to the first power was missing, we would need a placeholder coefficient called 0 in that position. All right. I think my student at home knows that based off of our first session together. So either way, we will be representing all of the coefficients right now. So it's 1, 6, 5, and negative 12. We're going to draw a nice line here. We're going to drop this guy down because, by the way, it always gets dropped down. And then we're going to just check each one of these. Let's start with positive 1. So positive 1 times 1, this is how you do it. Positive 1 times 1 is 1. And then we have 6 plus 1 is 7. And then we have positive 1 times 7. Well, that's going to be 7. And then we have and then we have 5 plus 7, pardon me, and that's going to be 12. And then we're going to have positive 1 times 12. Well, that, of course, is positive 12. And then we have negative 12 plus 12, and that is most definitely 0. Now, that is what you're looking for. If you get a 0 here, then whatever number here is one of the rational roots. Okay? So, in other words, 1 is one of the rational roots. Okay? Now, by the way, when they say rational root, it means a place where the graph, whatever the heck the graph looks like, crosses the x-axis. So we know for a fact that regardless of what this graph looks like, it definitely intersects the x-axis at 1. And it looks like my student already kind of took that into account right here. All right? But how did we know? Well, we tested 1. We knew that positive 1 is a possible value, and we tested it out. And sure enough, we got a remainder of 0. Now, that begs the question, what if we didn't get a remainder of 0? Well, that's easy. If you had not gotten a remainder of 0, then 1 is not a rational root. Okay, so we know for a fact that one of the roots, also known as zeros, is 1. Now, what's kind of nice about the teacher is that the teacher kind of makes things easy in that, like, the teacher's saying, list them here, right? Well, we're going to do that. We're going to list one of the zeros. And remember, by the way, my student at home, again, I think I already said this, but rational root, that is a 0. So for my student at home, the quicker you can relate these words together, in the context of problems like these, the roots are the zeros, and they also are the, quote, solutions. The roots are the zeros. Zeros are roots, and also sometimes you might hear the word solution. Okay? So just want to throw that out there. And definitely 1 is one of the roots, so we're going to put that here. Boom. Now, how do you find the other two? Well, you find the other two by recognizing that this thing really represents a new function, only with the exponent degree drop down. Now, what do I mean by the exponent degree? Well, the exponent degree here is 3, so this is going to have an exponent degree drop down 1 to 2. So this is almost like a different function, in a way, called x squared plus 7x plus 12. All right. Now, this happens to be a factor of this. Just to throw that out there, this thing times x minus 1 would give us this, to be clear. Now, if that's confusing, don't worry about it. It's not a big deal. What's mostly important is that you realize that you move from here to here now. And then you stare at this. And then you say, okay, well, this has a leading exponent of 2. This has a degree of 2. I know what to do with these. If I want to find the zeros, well, I just set it equal to 0, and I either factor it or I use the quadratic formula. My student and I were kind of completing the square a lot, and that's not the end of the world. However, I'm going to say let's use the quadratic formula because it's very straightforward. Okay. But first, let's double check and see if this is even factorable. It turns out that it is factorable because you have a 1 here and a positive 12 here. And you have to kind of multiply that first coefficient times this one. And just ask yourself, are there any two numbers that multiply to 12? Because 1 times 12 is 12, right? Are there any two numbers that multiply to 12 but add to 7? Well, absolutely. 4 times 3 gives you 12, and 4 plus 3 gives you 7. So there's no question that this could be factored into x plus 4 and x plus 3. All right, no question about that. And remember, if we're trying to find the zeros, we want to set this equal to 0. So our other two zeros are clearly negative 4 and negative 3. So I just put them right there. So we have our zeros, and my student did a good job. You put a dot at the x value of 1. You put another point at the x value of negative 3, and another point at the x value of negative 4. Now these are a little bit out of order, but whatever. Then it says y-intercept. Well, how do you find the y-intercept? Well, here's the good news. When the function's written in this like standard form like this, the y-intercept is super easy. The y-intercept is this number. The y-intercept is negative 12. That's all you need to know. When it's written in this standard form where it's like descending exponents and it looks nice and everything's separated by either addition or subtraction, that is the y-intercept. So that's why there's a point down here. Okay, so the y-intercept is negative 12. And then the teacher wants you to sketch the equation. You know, I'm assuming that since all we need are the zeros, the y-intercept, the sketch can therefore be somewhat rough. You know, it doesn't have to be perfectly accurate, I'm assuming, because this is not that much information. So I'm assuming the sketch can be rough. Now, the real question is, well, what the heck's going on with this graph? Is it a parabola? Is it not a parabola? Well, the bottom line is, anytime you have a function that is of an even degree, like for example, if you had something like y equals x squared plus 2, if the degree of the function is 2, well, that means that the end behavior of the function points in the same direction. And for the record, if that was y equals negative x squared plus 2, where the leading coefficient was negative, we'll say plus 2, then the end behavior for that would be down. But notice what these two have in common. What these two have in common is that the end behavior points in the same direction. Now, of course, we're going to want to contrast that with what happens when the degree is odd. So when we have a function such that the leading degree is odd, then it's like this. So this one has a positive leading coefficient and an odd degree. So you want to think of it as like a line, like a slope. All right. So imagine you had a line where like the slope is positive here, you know, because this is a positive leading coefficient. So what do you do when you have a positive slope? It's a line that goes up from left to right. Well, in the same way, this function is going to have end behavior that sort of goes down to the left and up to the right. Okay, so the best way to remember that is, again, think of a line, think of the leading coefficient as though it's the slope. Don't worry about the number so much, worry about the sign. And it's a positive one right here, right? It's positive. So you could associate that with a positive slope. Okay, of course, over here, we have a negative one in front, right? So I'd like my student at home to associate that with a negative slope. and therefore the end behavior would be like that. Okay? Now, what's going on in between this? I don't know. I mean, it could be, I don't know. But the bottom line is the end behavior is like that. So the truth of the matter is this is an odd degree. The leading coefficient is positive. So we know for a fact that the end behavior is going to be like that, and it's going to be like that, right? We also know that it's got a y-intercept of negative 12, which is like right there. So it's going to be something like, the following. Something like this, where it goes up, it cuts through, it swoops back down, it goes all the way down, it picks up that y-intercept, and then it cuts through this thing, and then it goes up forever. Now that is obviously the ugliest graph anyone has ever drawn. Okay? But hopefully you get it. That's basically how it works. All right? Now, with regards to how high this goes, well, that's a separate question. How low this goes, well, we definitely know that, right? But I have a feeling sort of honing in on how high this goes is beyond the scope of what my student is learning right now. All my student, I believe, needs to know is that it cuts through, of course, the x-intercepts, the y-intercept, this x-intercept, and the end behavior is such that it goes down here and up here because of the positive leading coefficient. Okay, so now we're going to focus on the next problem. Okay, so let me white all this out. And also, by the way, for my student at home, I'm seeing that it looks like your teacher wants you to write the actual coordinates. Okay, so let me backtrack, and we will call this. These are things you got to just pay attention to. We'll kind of rewrite these, so it's the coordinates, of the x-intercept. And they should be 0, negative 12. Hopefully that makes sense. Let's see. So, rational root theorem for this one. Well, once again, we're going to want all the factors of positive 160 over all the factors of positive 2, yes? So that's how you find the possible roots, right? The possible rational roots. So we are going to go on a little mission. We definitely know it's going to be plus minus, And let's see, all the factors of 160. Well, here they are. They are the following. Certainly, it's a lot. It's definitely a lot. So we have 1 in 160. By the way, I'm using an app called Simple Factors. Highly recommend, because nobody would want to work this out. I mean, you could, but it's annoying. So we have 4 and 40, 5 and 32. Oh my goodness, running out of room. Look at this. 8 and 20. Ugh. And then I'm going to, when you run out of room, just go up with it. That's my recommendation to you guys. So it's also 10 and 16. And all the factors of 2, well, obviously, 1 and 2, right? So we're going to have to sort of make sense out of all this. Here are all the factors. First of all, it's going to be positive over negative, right? So let's consider all possible numerator numbers over 1, correct? Because that's easy, right? Whenever you have a denominator of 1, it is just itself, right? So 1 over 1 is really just 1. 4 over 1 is really just 1. So we're just going to sort of rewrite all of the factors in the numerator there. So we have 1, 2, 4, 5, 8, 10, 16, 20, 32, 40, 80, 160. Now we have to take into account all of the numerator things over 2. Now we're going to get some repeats, just as a heads up to you. There's going to be some repeats. So we don't write the repeats, but let's do it. So we're going to have 1 over 2, which is new. We're going to have 2 over 2, which is 1. We already took that into account. We're going to have 4 over 2, which is 2. We already took that into account. We're going to have 5 over 2. We're going to have 8 over 2, which is 4. We already took that into account. We're going to have 20 over 2, which is 10. We already took that into account. We're going to have 32 over 2, which is 16. We already took that into account. We're going to have 40 over 2, which is 20. We already took that into account. We're going to have 80 over 2, which is 40. We already took that into account. We're going to have 160 over 2, which is 80. We already took that into account. So actually, it's very nice. We just have like 2 extra fractions as a result of that. But the bottom line is, here are all the possible rational roots. So, just like last time, we are going to figure out which one of these roots, or ones of these roots, would create a remainder of 0 when using, synthetic division. So, first, let's double check, is this in descending order of exponents? Yes. Now we can focus on the coefficients, and we could just write them. So the coefficients are 2, we have -1, we have -42, we have positive 16, and a positive 160. Set up the structure, drop this down, why? Because we always do, and then move into testing these numbers. Let's start with 1. So if we tested out 1, that would be 1 times 2, which is just 2. And then we add -1 plus 2, which is just 1. And then we say 1 times 1. Well, that's just going to be just 1. And then we have -42 plus 1. Well, that's -41. And then we have 1 times -41, which is -41. And then we have 1 times, or actually we have to add 16 plus -41, and that is a -25. And 1 times -25 is -25, and that is certainly not 0. So 1 is out. 1 is not a root. So you would go through the motions. Now what I'm going to do is cheat, just for the sake of saving time on this video, because I think my student understands that process. So student at home, please understand that you would just keep doing that until you find that that remainder of 0. And as far as I could tell on my calculator, I think -4 would work. So let's just double check that. Actually, -2 would work. -2 would work. And I think -4 would work for that matter. But let's just double check. So -2 times 2 is -4. When you add -1 plus -4, that's -5. -2 times -5 is positive 10. -42 plus 10 is -32. -32 times -2 is positive 64. And then when you add those, that's going to be 80. And then -2 times 80 is -160. And that would most definitely give us the remainder of 0. So we know for a fact that one of the zeros is -2, 0. Okay, remember, we're going to write everything in the coordinate form, so one of the zeros is -2, 0. I'm not going to write that right now, but there it is. Okay, so we already know that that works. And then, what do we have here? We have a new equation, or a new polynomial to work with. Now, for the record, for my student at home, you could stick with the original one and keep plugging in stuff. I'm pretty sure that -4 is going to work as well. And we're going to kind of work with -4 in a moment. So had you stuck with the original lineup and then just kept testing, you would have discovered that, there are other roots that would work. And those would be the answer. However, I'm actually going to use this one because you could use this one as well. It should work out here as well. So we're going to sort of do another thing where we represent these new numbers. Okay. Because we can. And do the same thing. Now, I'm going to go ahead and just try -4 right now and see what happens, because according to my calculator, it looks like -4, 0 is a 0. So -4 times positive 2 is negative 8. When you add negative 5 plus negative 8, that's negative 13. Negative 4 times negative 13 is positive 52. And then when I add negative 32 plus positive 52, that is 20. And then negative 4 times positive 20 is negative 80. And that is very much our amazing root. That's another root. So we're going to put that here. Negative 4 comma 0, which really belongs here, but I don't feel like zooming in. So just know these are the zeros so far. Okay, now one of the reasons why you're going to want to work with the new lineup is because it whittles things down to these three numbers. Once you get three numbers, you're back in familiar territory. I'm just going to use g of x because why the hell not? So we have 2x squared minus 13x plus 20. Okay, so that's based off of the latest lineup of three numbers. Once you get it to three numbers, you're back into this nice quadratic trinomial situation, which my student at home probably has a lot more familiarity with. Okay, and what do we do with quadratic trinomials? Well, it's easy to find the roots here. You know, you just set the freaking y equal to 0, and then you solve for x, solving for x. How do you do that? Well, first of all, you see, can I factor it? If I can factor it, I'll just factor it and solve it from there. If I can't factor it, I'm going to bust out the quadratic formula. Okay? Now, how do you know if you can factor it? Well, you have to look, once again, for the magic number. What's the magic number? The magic number is what you get when you multiply the first coefficient times this thing, and that is 40. And then you ask yourself, are there two numbers that multiply to 40 but add up to negative 13? And the answer to that is yes. Okay, it is negative 8 and negative 5. Negative 8, negative 5. All right. So the question is, what do you do with that information? So what you have to do, when you have a leading coefficient that's like the absolute value of which is greater than 1, then you must kind of approach it a little bit differently. And the way to approach it is you just rewrite it, only always put plus here, empty parentheses, x. I'll say it again. Rewrite it, always put plus here, empty parentheses, x. And then finish it, 20. Okay? This is the way that I would recommend. There's different ways of doing this, but this is the way I would recommend. Always put plus, empty parentheses, x. And then you put in here the two numbers that you just got, negative 8 minus 5. Once again, negative 8 times negative 5 gives us 40, which is our magic number that we got from multiplying 2 times positive 20. And negative 8 minus 5 gives us that negative 13. Okay? In a way, we took this middle coefficient and we exploded it like a piece of popcorn in the microwave. All right? Then you distribute the x to each of these. So this is going to become the following. It's going to become 0 equals 2x squared minus 8x minus 5x plus 20. Okay? 2x squared minus 8x minus 5x plus 20. So again, what have we done? We had the negative 13x. Well, we just exploded it and turned it into negative 8x, negative 5x. And if we were to combine these two like terms, well, we would just be back at negative 13x. So we haven't done anything illegal. We haven't changed the value of anything, have we? We've preserved the value. Now, you might be wondering, okay, why are we doing this? Well, we can now factor by grouping. Factoring by grouping means focus on two terms at a time. Okay. Now, the first two terms are such that we could factor out a 2x as a GCF. Okay. Focusing on the first two terms only, we could factor out a 2x from these guys. And then you would have x minus 4. And then you go to these guys and ask yourself, what is the GCF of these two? The GCF of these two is negative 5. So you're going to factor out a negative 5, and that's going to give you an x minus 4. All right? That's called factoring by grouping. You take two terms at a time, find the GCF of just those two, factor it out. Then you look at these two, take the GCF of these two, factor it out. Now, if all has gone well, and if this function is indeed factorable, which we know it is, this parenthesis should match this parenthesis. So on the next step, what you're going to want to do is you're going to want to, rewrite the 0. Teachers like that. And then what do? You make two parentheses. What's one of them going to be? The repeated parentheses. Right? Put it right there. What goes in here? Everything else. That's what goes in there. What is everything else? 2x minus 5. So for my student at home watching, rewind that process. Look up, if you need practice with this method of factorization, you might want to look up a video that just says factoring quadratic trinomials with, a leading coefficient of absolute value of which is greater than 1. And you'll see quickly, the wording on Google might be different, but, any quadratic trinomial that can be factored where this number is such that the absolute value of it is greater than 1. It could be 2, could be 10, whatever. Those are the ones you're going to want to check out on Google. And more specifically, this is called factoring by grouping. If my student wants more practice with factoring by grouping, quadratic trinomials, just Google that and find YouTube videos on that. All right. So anyway, the question is, what do we do with these guys? Well, at the end of the day, hopefully my student remembers that you can sort of just treat these as separate equations and set them both equal to 0. So that equals 0. We're going to have x minus 4 equals 0. And then, solving for x over here would give us 5 over 2. And solving for x over here would give us 4. So those are the other two zeros, 5 over 2 and positive 4. So we're going to go all the way back up here and just list that 5 over 2, comma 0, and 4, comma 0. All right, so we have negative 2, comma 0, negative 4, comma 0, 5 over 2, comma 0, and 4, comma 0. So let's write that in this sheet. First of all, it's going to be parentheses, so I like to just do that first because I like to approach these methodically. It's definitely going to be 0. And then we're going to have negative 2, negative 4, 5 over 2, and I believe it was positive 4. Okay, hopefully that makes sense. Let's double check. Sometimes it's wacky. Yeah, 4, comma 0. All right, so good. So that's how we find the zeros. Now the y-intercept is the easy part. That's just right here, positive 60. So that's going to be 0, comma, positive 160. The teacher is expecting you to graph that. Well, what does it go down to? Negative 6, negative 8, negative 10. There's no way in hell we're going to be able to graph that y-intercept of positive 160. That's just miserable. So we're going to make a rudimentary graph right here. Let's say it's totally, what's it called? Not drawn to scale. Okay. And therefore the window is going to be such that we have a maximum y value of positive 200 and a minimum y value of negative 200. And let's kind of look at the domain that we want to represent. It goes from negative 2, negative 4, 5 over 2, which is 2.5, by the way, and positive 4. So honestly, dude, we're just going to call this negative 10 and call this positive 10. Totally not drawn to scale, right? It goes up 200 over 10, so it's totally not drawn to scale. All right. In fact, it would be like super narrow, but we need to like see it, right? So the bottom line of it is we can just put our kind of x, intercepts here. Definitely we have one at -2, 0, which would be right around here, yeah. And -4, 0, which would be like right around there. And then we have 5/2, which is like 2.5, and then 4. Okay, so it's kind of like that. Let's imagine that's -5, and imagine that's 5. Now, I'm not going to draw the actual coordinates here because it would get a little messy, but hopefully my student at home realizes that's -2, 0, that's -4, 0, that's 2.5, 0, and that's 4, 0. Okay. We also know that the y-intercept is 160. That's going to be 100, so 160 is going to be right around there. So you could just kind of draw that stuff, right? And then you have a leading, or a degree rather, that is even, so the end behavior is going to be pointing the same way. We also have a leading coefficient that's positive, so that means the arrows are going to be pointing up, right? The fact that this 4 is even means that the arrows are pointing in the same direction, and the fact that this leading coefficient is positive means that they are both pointing up, okay, as a review. So we know that, in other words, this is happening for sure, okay? Now, what you can do then is you can trace it down, so it's like that. It crosses through 160. It goes down here, and then it goes up. Notice how I drew the arrows first to sort of prime my brain into recognizing that that's happening at the end, and then it's sort of a matter of connecting the dots after that. Don't forget to go through 160, and then you go through there. Okay, hopefully that makes sense. That's how you do that. Okay, for this kind of a problem where they give you a function and then they tell you that 2i, I believe this means that it's a root. So if I'm not mistaken, unless I'm reading it wrong, I'm pretty sure that this means that it's a root or a 0. Now what that means is, basically what that means is, if you were to sort of try to solve for x in this long polynomial, of course, you'd have to set it equal to sort of 0, and then take it from there. And it is the case in this problem that 2i happens to be one of the zeros, which means that one of the factors, if you were to take this whole thing and factor it out, one of the factors would end up being x minus 2i times, the rest of it, some other function, to be honest. So, in other words, we know for sure that this parentheses right here is a factor of this, and it's like this factor times whatever else would give you this thing, all right? Now, there's something called the conjugate pair theorem that applies to imaginary numbers. When you have an imaginary number that is a root or a 0, then you know beyond a shadow of a doubt that not only is x minus 2i a factor, which is right here, x minus 2i is a factor, but we also know that x plus 2i therefore has to be a factor. So if you follow my reasoning process, you knew that 2i is a factor, therefore 2i is a root rather, therefore x minus 2i has to be a factor. And since x minus 2i is a factor, then we know for sure that x plus 2i also is a factor, and that's going to be multiplied times some function. We could say some other factor. Function or factor, really, depending. And the bottom line is, when you multiply this times the other thing that we don't know yet, it would end up equaling this. All right. So really, if we want to find like the other zeros or the other roots in general, we would have to figure out what this thing is. All right. We'd have to find out what this thing is, because we already know that 2i is a root. We also, by the way, know that negative 2i is a root as well. In fact, we're going to write that down. So we already know that 2i is a root because that was given. We also know that negative 2i is a root as well. So then the question is, what are the other roots in this thing? And we'd have to investigate this scenario in order to figure that out. So that is what we're going to do. Now, you might be wondering, well, how will we find out what's going on over here? Well, it will always be the case that when they give you an imaginary root, it will always be the case that this conjugate pair theorem applies, and it will always be the case that you can absolutely multiply these. And that's going to become x squared, let's see, it would be plus 4 times this. Now I'm going to replace this with a big fat green question mark. All right. Big question mark, big question mark. Now you might be wondering, well, how did I get from here to there? And for my student at home, you might already know that. But I'm going to go over that really quick. Well, first of all, you could always FOIL it. First times first, outer times outer, inner times inner, and last times last. You could also realize that this is really the structure that you would get if you were to factor the difference between two squares. So you might not know what I'm talking about. Let's forget all of this and simply remember the following. A squared minus b squared equals a minus b times a plus b. So in other words, if I had x squared minus 16, well, this is secretly x squared minus 4 squared. And that most definitely equals x minus 4 is x plus 4. All right, so it is true that whenever you have a perfect square minus another perfect square, like this, it can therefore be factored in that way. Now, at a certain level of experience, you start recognizing when this situation is going on, and you realize that there is occasionally some practical value in moving from this position to this position. Now, you could just FOIL it. You could just go x times x, blah, blah, blah. You could do that whole thing, and then you would end up with this. Or you could sort of get to the advanced stage where you just kind of recognize the structure, because this is a binomial, and this is the conjugate of that binomial. And you can realize that when you multiply these, you get that. Well, in reality, that's what's happening over here. Let's investigate this. We're going to investigate that in slow motion. All right, so this would be x minus 2i times x plus 2i. And when we really focus on this, in the same way that this x times this x gave us this x squared, so this x times this x gave us this x squared, well, this x times this x is going to give us x squared. And if you analyze what happened here, we had a 4 times a 4 gives us 16, and that ended up going over here. So we had a minus 16 over here. So whenever you have the difference between two squares, it will always be subtraction here, right? And all you have to do is actually just focus on what this number times this number is, and therefore it will be negative whatever that product is, the negative version of 4 times 4. So we know that it's going to be minus something, so I'm just going to write that, and I'm going to make some parentheses as a placeholder. And now my question is, it's going to be 2i squared, right? So it's going to be 2i squared. Now, on the next line, we're going to keep the x squared because that's still there. And it's going to be minus whatever the heck 2i squared is. But if you think about it, anytime you have a product raised to a power, in a way, you could think of sort of distributing this power to there and there. You could think of applying that exponent to both of these numbers. That's honestly a law of exponents that I would strongly recommend my student at home makes sure he's familiar with, so that we would have 2 squared, and then we would have I squared, and then we'd have to ask ourselves, what is this? Let's rewrite the x squared first. So we're going to have x squared minus, still going to keep it in brackets because I want to keep everything organized. What is 2 squared? Obviously that is 4. What is I squared? Well, I squared, hopefully by now, my student at home knows that I squared is negative 1. So that's what's happening over there. Now, once you've done that, we could sort of write the next line, which is x squared. Now it's minus, and this is going to be a negative 4, correct? So we would have minus negative 4, which is really plus 4, okay? So that is how I got this x squared plus 4, all right, in case there's any question about it. So if you have to sort of rewind that and look at it again, etc., then go ahead and do that. But at the end of the day, quick recap. We know that 2i is a root or a 0, therefore x minus 2i must be one of the factors of this thing. If x minus 2i is a factor of this whole thing, due to the conjugate pair theorem, then x plus 2i must also be a factor of this whole thing. So for me, I just find it helpful to go ahead and write that. All right, we have these 2 parentheses that set equal to 0. We have these 2 parentheses. And then we know that, this stuff times whatever the heck this is would give us the blue function, right? So now we're on a new mission to find out what this is right here. So we did multiply these two by just applying all the previously mentioned insights, where this ends up becoming x squared plus 4. So it's going to be x squared plus 4 times whatever this is. So we're going to go on that mission, like I said, to find out what the green question mark is. And you might be wondering, how do you do it? Well, let's use the insight that this times this equals this whole thing. So I'll say it again, this times this equals this whole thing. So therefore it must be true that this whole thing divided by this thing is going to give you that. So I'll say that again as well. This whole thing divided by this thing is going to give you that. That's the fundamental insight that really comes into play. And therefore, when it comes to these problems where they give you an imaginary root, you actually have to use long division. You're going to have to use that polynomial long division. Now the dividend is x squared or x to the 4th power plus 4x cubed plus 7x squared plus 16x plus 12. You want to make sure that all the exponents are in that nice descending order, all right? And therefore every potential exponent is represented. It is true that all of these, exponents 4, 3, 2, 1, and actually 0 over here, they are all represented, so we can feel totally comfortable just sort of rewriting that dividend. So there's the dividend right here. I just wrote it. Took this blue polynomial and made it the dividend. And what are we going to divide it by? Well, we're going to divide it by this, because remember, we want to find the green question mark. So x squared plus 4 is the divisor. Now when we write x squared plus 4, we want to make sure that that's written in a way that will allow us to do long division. The truth is that x squared plus 4 could be rewritten as x squared plus 0x plus 4. Now, in the same way that we demanded that this polynomial has every possible exponent in descending order represented, well, we have to do the same thing here. We need that exponent of 1 represented. So it could say 2, 1, and then really this is x to the 0 power. You can imagine that, because anything to the 0 power is just 1. So this is x to the 0 power, which is 1. times 4, which is just a 4. So we want to represent this as the divisor. So it's x squared plus 0x plus 4. And for my student at home, yes, unfortunately, your long division game must be on point, right? So it's pretty easy once you get the hang of it. Obviously, it requires some practice here and there. But basically, you just focus on the first term in each of these, and you ask yourself, x squared times what would give me x to the 4th? Well, x squared times another x squared would give me x to the 4th. Notice how I write x squared perfectly above this x squared. So when you're doing the quotient, you want the exponents to match each other, okay? And then I go through the motions. X squared times this x squared certainly gives me x to the 4th. We have 0x, 0x, which is really just 0, times x squared. Well, that's going to give me 0, we can say x to the 3rd. Now, the fact that I'm writing x to the 3rd, x times x, I'm just kind of making it beautiful so that the x to the 3rd is underneath this x to the 3rd, but at the end of the day, this is just 0, so please keep that in mind. And then we have 4 times x squared. Well, that's most definitely going to be plus 4x squared. And then what do you do in long division? Well, once you've kind of did that multiplication thing, you then subtract this whole thing. Now, when you subtract the whole thing, it really just changes the sign. So this becomes negative, this becomes minus. So x squared minus x to the 4th minus x to the 4th is just 0. 4x cubed minus this thing, well, that's just 4x cubed, actually. And 7x squared minus 4x squared is positive 3x squared. And in the same way that you would do so for long division with decimals, you then drop the next thing down. So that becomes plus 16x. We're going to leave the 12 up there, just kind of minding its own business. I'm going to draw a little arrow just to showcase the fact that we dropped that down. And then it's the same process with this and that as the new dividend. So x squared times what gives me 4x cubed? That's going to be plus 4x. And then I go through the motions once again where, it's x squared times 4x. Well, that gives me 4x cubed. Then I have 0x times 4x. Well, that's going to give me plus x squared. Then I have 4 times positive 4x, and that's going to give me plus 16x. And then we subtract this whole thing, which really just, again, changes the sign of everything. So changing the sign of everything would make it so that it's 4x cubed minus 4x cubed, which is just 0. It's going to be 3x squared minus 0, which really is just 3x squared. And it's going to be 16x minus 16x, which is just 0. I'm actually not going to write that. I'm just going to leave it alone for now. And then we have this positive 12 that should be dropped down so that it's down here. So it's really a plus 12. Okay, so we have 3x squared plus 12 left over. Once again, these canceled. 3x squared minus 0 is 3x squared. 16x minus 16x, because remember, we would distribute that negative into this term. That's going to be 0, so we don't even really have to write it, And then we drop the positive 12 down, so what we're left with is 3x squared plus 12. So then you ask yourself, x squared plus 0x plus 4 times what would give me 3x squared plus 12? And hopefully it's clear that multiplying this whole thing, it's really just x squared plus 4. Hopefully it's clear that multiplying this whole thing by 3 would give us 3x squared plus 12. I'll leave it to my student at home to just sort of double check that. Well, we'll double check it now. Let's test it. X squared times 3 is most definitely 3x squared. 0x times 3 is just 0. I'm not going to bother writing that at this point. And then 4 times this 3 is a positive 12. What happens when you subtract this whole thing from this? Well, it's 3x squared plus 12 minus itself. Well, of course, that would be 0. So we have a remainder of 0, which is totally what we wanted. If you don't have a remainder of 0 after this long division process, then something went wrong. All right? So we found our green question mark. We took this blue thing, we divided it by this, and we found our green question mark. The green question mark turns out to be x squared plus 4x plus 3. So I'm going to go ahead and represent that over here. By the way, I know the music might be loud, so I apologize for that. I'm at a Starbucks now. I've migrated my position due to my tutoring schedule. So get rid of some of this stuff. All right, looking at these, because it's the green question mark, that's what we were talking about before, and that's going to get x squared plus 4x plus 3. I'm going to be thorough and just fill up both of these parentheses with that. X squared plus 4x plus 3, x squared plus 4x plus 3. So the one that we're really interested in is this line right here. So let's just kind of summarize the truth. And the truth is that this whole expression could totally be factored into that. But we're not done yet, because at the end of the day, we want literally all of the zeros of this. We already know that this parentheses sort of tells us that one of the zeros is 2i and another one of the zeros is negative 2i. That's what this part tells us. But what about this part? What about the green? How could we figure out, what the zeros are to this larger, expression or function really, by working with this one? Well, it turns out that this can be factored. And I want my student at home to realize that you want to first check and see if you have a trinomial, and I kind of said this in the last slide. If you have a trinomial where the degree is 2, first thing you want to check is just, can this thing be factored, right? And if it can't be factored, like I said in the last slide, you just use the quadratic formula. That's what you have to do. Use the quadratic formula. Now it turns out that this can be factored, and the way that I know that is that we have an invisible 1 in front of here. Obviously we have a positive 3. And when I try to scope out 1 times 3, that gives me a 3. And then I ask myself, are there any two numbers that multiply together to give me 3, but add together to give me 4? And the answer is absolutely. 3 and 1, when you multiply them together, you get 3, and when you add them together, you get 4. So this could totally be factored into x plus 3 and x plus 1 rather. And we could drop this one down as well. x squared plus 4 right there. Now we already know from before that this parentheses lets us know that the roots include 2i and negative 2i, but these guys right here let us know that the roots are also negative 3 and negative 1. Okay? So these are the amazing roots to this function right here. Now you might be wondering, okay, well, how do I graph this when I have these imaginary roots? Well, the good news is if you're drawing like a very rough graph, you can kind of ignore these, right? You can kind of ignore these. It's really these that you want to focus on. And obviously we're going to want to focus on that y-intercept, right? So don't forget the y-intercept. So I'm just sort of assuming that the teacher wants you to provide a rough draft graph for this problem, although I am taking note of the fact that no graph is provided next to it, so I don't know. Maybe my student at home should know. One thing's for sure, we have a y-intercept of 12. So we could kind of just write that, you know. We also know that there are moments, you know, where it crosses the x-axis. In fact, I'll even rewrite this so it clearly says, you know, negative 3 comma 0. Sometimes I forget that, admittedly. We have negative 1 comma 0. So we know that these points are on the graph as well. And if you really want to sort of show the teacher that you know what you're doing, you could let her know that the y-intercept is literally 0 comma 12, right? All right. I have a sense that the teacher wants my student to definitely write these points. And then, yeah, just plot these, right? Negative 3, negative 1. So we're going to have a point, you know, around here and here, where we have negative 3 right there and negative 1. So you still might be wondering, it's like, okay, great, I just wrote these points down, but what does the freaking graph look like? Well, at the end of the day, it is a function that has an even degree, since the largest exponent represented is 4, which is even. So we know that the end behavior is pointing in the same direction. We also know that the leading coefficient is a positive 1 right here. Since it's positive, that means that the end behavior arrows are pointing upward. So you ask yourself, okay, well, what sort of U-shaped thing would pass through this point and also this point? Well, I'm sure my student at home would soon realize that it would be something like that, all right, but it goes through. It's the ugliest U-shaped thing ever, but you get the idea. It cuts through and it goes back up, but it goes through 12, right, and it goes forever. In that direction, it goes forever in that direction. So once again, don't pay attention to my ugliness of the U-shape. I'm just kind of winging it right now. And, you know, keep in mind, you could always graph this in your graphing calculator. You could actually take this, put it in your graphing calculator, and get a sense of what the graph looks like. It would definitely be something that is something of a U-shape that cuts through these points for sure. All right. And again, at this stage in the game, I'm pretty sure the teacher is not really worried about how accurate it is, as long as you get these 3 points and as long as you get the end behavior correct. So that's how you do these problems. I hope this was helpful for my student at home. I hope it was helpful for anybody else who watched it. Kind of tricky stuff. It's Algebra 2, you know, so it's certainly not as easy as Algebra 1, obviously. Pretty tricky. But anyway, if my student understood it, good job. You know, please rewind, slow it down, or speed up the YouTube video as much as you have to make the video easier to watch. And good luck. I will see you all soon.